Hey, welcome everyone. Today we have Karim here to talk about canonical general relativity. He's from the University of Bristol, and there he is also a member of the Bristol Philosophy of Physics group. Yeah, take the floor.
Thank you very much. Thanks for the invitation. It's been really wonderful visiting the group and chatting to new people, old people, and learning about your work. Exciting for me to have this wonderful group, not so far from Bristol. And so today, sorry that I gave a slightly elliptical title. Hopefully make a little bit more sense why I called this Spirit about Dogma later. So some of this work is kind of material I've been preparing for second volume of the book, which I'll say a little bit about a bit later. With Sean Gribb. This is part of a project that's been going on for
just there's a chair, use a chair. I'll get a bit closer to Karim.
So it's a project we've been working on for some time, and related to the problem of time and quantum gravity. And what I wanted to do to kind of get you into the swing of things and to hopefully give you some kind of idea why I gave the book such a strange title is just do a bit of historical analysis, and we're in the right place for this. And just kind of going back a little bit and thinking about particularly the rhetoric of science, much as the actual detail. And that's where the spirit of the dogma will come from. And then I'll give you a little bit of detail about the canonical framework, introduce particular motivation for a way of thinking about symmetry through Dirac, dogma, spoil a little bit, and then talk about the problem of time, and then our kind of proposal that we can solve the problem of time without the Dirac dogma process of working on. But as I said, first I'll give you a bit of a historical background. So in 1967, an introduction to a very famous paper where he derives the Wheeler-DeWitt equation, Bryce DeWitt gives a little kind of survey of the motivation for where the Hamiltonian or canonical framework for general relativity came from. And so he looks back all the way to the 1950s in particular, and to work of Bergman, Peter Bergman, and Paul Dirac. And so Bergman, along with a kind of a whole school of people at Syracuse University, I went to Sicily, so I want to call it Syracusa. They worked on the program of canonical approach to gravity in Syracuse. There was also Dirac ploughing a kind of lowly furrow, working on his own. There's really three teams, and then there's the famous ADM partnership in Princeton. Anyway, DeWitt, who's kind of closer to the ADM group and to Wheeler, describes the history this way. So he says, looking back from 1967, Dirac and Bergman set out on the classical canonical road in search of a Hamiltonian, despite the fact that canonical methods, by singling out time for special treatment, run counter to the spirit of any relativistic theory, above all, such completely covariant theory as general relativity. And so DeWitt says similar things later.
Sorry, I think that is not sharing properly.
Slides, yes.
Sorry.
That's right. That was me. Sorry, I can see us. Yeah, great. Thanks.
So the idea is that the Hamiltonian approach to general relativity, although it's got this attractive feature that it's got a natural path towards a quantum program for quantum gravity, which people like DeWitt were interested in, as were Bergman and Dirac, it has some kind of tension with the kind of essence, spirit, kind of basic feature of general relativity. And what I did, which I won't go through, is actually trace this idea of the spirit of general relativity back much earlier to its first kind of usages. And it gets used lots of different ways over the course of a few decades, and then it kind of stabilizes to mean something like the kind of conceptual features of background independence or coordinate theory. And so the idea is that by being 3 + 1 rather than 4, the approach is intention of the spirit. And even someone like DeWitt, who did so much to kind of develop the canonical approach, particularly the quantum version of the canonical approach, is worried about this intention of the spirit. Probably most pointedly, Stephen Hawking, who's really not a fan of the 3 + 1 Hamiltonian approach, kind of crystallized this into an attack on the kind of cogency of the program. In the canonical approach, one introduces a family of space-like surfaces and uses them to construct a Hamiltonian and canonical equal time commutation relation. This approach is favored by a number of authors because it seems to be applicable to strong gravitational fields and is supposed to ensure unitarity. However, in the split into 3 dimensions and 1 time dimension seems contrary to the whole spirit of relativity. So you find this after this all the time. I think I found 10 or 15 people saying, look, you could do this whole Hamiltonian thing, but that's just not in the spirit of general. Not in the spirit of Einstein's ghost will like stalk you down and worry you because you've done something wrong. And so what I thought was interesting is that the way that in the kind of rhetoric of debate between the covariant and canonical approaches, you find that in the canonical approach, they actually turn this around. And this is my kind of way of thinking about particularly the problem of time, or the canonical response to the problem of time. And so the particular quote I'm going to give you, and I can find others that are similar in nature, comes from Ashtekar and Horowitz. And they use the particular features of general relativity, so canonical general relativity, particularly this idea that in canonical general relativity, gauge transformation, the time evolution becomes a gauge transformation of a particular approach that leads to the problem of time, as a kind of rhetorical riposte. Say, look, we haven't just got the spirit of general relativity, we've got like the kind of real nature of general relativity, the real kind of kernel of it was that time was gauge transformation. And so we haven't kind of broken the spirit of the theory, we've embraced it even more strongly than in other approaches. Let me read this one. The evolution of the system is via infinitesimal canonical transformations generated by a function on phase space which vanishes on the constraints of manifold. Any infinitesimal canonical transformation generated by a function which vanishes on the constraints of manifold is normally regarded as a gauge transformation. This is the thing that I'll talk a bit about that comes from Dirac. The idea is that there's a particular type of functions you find in a Hamiltonian theory that has gauge symmetries, constrained Hamiltonian theory. And these functions, the constraints, generate particular orbits in phase space, particular directions in phase space. And Dirac had an argument that we should always treat these directions as unphysical, as just moving between different representations of the same physical state of affairs. So what they're doing here is pointing to this kind of criteria that Dirac developed and kind of embracing it in relativity too. So this means that in particular, we'll find is that the Hamiltonian itself becomes one of these constraints that generates that physical direction. This means we may think about evolution as the unfolding, we may think of the evolution as the unfolding of a succession of gauge transformations. The multidimensional character of time is just a reflection of the large group of smooth transformations on the space-time manifold, transformations which are, from the point of view of general relativity, pure gauge. So we get from the canonical approach involves splitting into space and time. This violates the spirit of the theory. To the canonical approach involves turning time into gauge, and this means the theory really truly implements kind of diffeomorphism of variance or background. It's a peculiar situation, this much studied problem of time. And I want to say a little bit about how you get to the problem of time and whether there is an alternative way out. In particular, whether we can keep the spirit of general covariance without the Dirac dogma, without this idea that constraints always generate gauge symmetries. So what I'll do first is talk a little bit about the unfortunately complicatedly named hypersurface deformation algebroid, which is a mathematical kind of part of the theory which represents how the symmetries are implemented. And I'll do this in hopefully a fairly accessible way. So taking some pictures, and then talk about how this leads to the problem of time, and then talk about the proposed solution that Sean and I are working on. If you want me to explain anything more clearly or slowly, just stop me. I'm really happy to get questions during the talk. Yeah. So this it'd be best for us to wait, but in this context, it means evolution, the evolution equation generated by the Hamiltonian. But we'll come. This is certainly we'll return to. So when we get back to it, hopefully it should be pretty clear. I mean, in some sense, it should be pretty clear that saying that doesn't really make sense. But this is the standard view in the literature that you should treat the directions where the dynamics are generated and the directions in which the gauge transformations exist as the same directions, which seems, to me at least, a reasonable reductio of an approach to the formalism, but it's standard view of people taking literature. We'll come back to this. This is that's in essence is the problem of time. Of how can it possibly be the idea? How can it possibly be the case that time can be a gauge transformation?
Maybe it's a similar question, but I feel like over the years I've lost track of what people mean when they say gauge, unless they mean log.
We certainly will clarify that. Very precise. Well, hopefully. Okay, so let's forget a bit about problem of time for the time being and just think about the theory. So I've been saying Hamiltonian general relativity. I haven't told you what that is or how it was derived or what it is. And so the standard thing to do is to derive it by taking the Einstein-Hilbert action and then following the passage to the Hamiltonian formalism in a slightly more complicated way, but using the same idea of defining momenta, defining a phase space, and you can write the theory as a Hamiltonian theory. Dirac was first in 1958, 1959. Was an interesting question asked by Wheeler a little bit later in the 70s was, could we actually derive this formalism without having without going through the Einstein theory? I mean, in this case, he's talking about the Hamilton-Jacobi equation, but essentially it's the same. Could we derive the Hamiltonian formulation of general relativity without looking at the Lagrange, without kind of having the Lagrangian theory, without having the Einstein-Hilbert action first? And the answer is yes. And this incredible paper by Hodgman, Kukash, and Thébault, what they showed is that there's a very kind of special structure to the way that these constraint functions relate to each other, functions that encode symmetry within the theory, which kind of picks out general relativity, or certainly a class of theories which includes general relativity. If you add in extra conditions, you can actually then get general relativity. But what's really important for us is not the extra conditions, but the idea that theories which have a particular type of symmetry, where you have hypersurfaces embedded in a geometry of one dimension higher, and you have an ability to deform these hypersurfaces and get the same kind of underlying geometrical facts, that picks out a class of theories that includes general relativity. So what Hodgman and Kukash and Thébault did, in particular what Thébault did a little bit earlier, was show that any theory in which the theory is invariant was defined on slices of a four-dimensional space-time, spatial slices that cut a four-dimensional space-time up, and it's invariant under how those three-dimensional slices are embedded in the four-dimensional geometry, will have a particular symmetry structure, and general relativity is part of that class. And most of what I want to talk about today is the structure of this algebroid that has this particular feature of deformation.
So can I ask?
Yeah.
Does that have something to do with the spin? Or this,
No, there's no spin at this level. It's just the three-dimensional geometries embedded in a four-dimensional geometry. It'd be interesting how you would include a spin algebra, but I don't know. So I'm not going to go through how they did the derivation. I'm just going to write down the equation, and then we're going to look at it. But the idea is that you can think about this as either coming from Einstein's theory or coming from this more abstract argument that you can derive a particular formulation of gravity, which applies almost in exactly the same way as general relativity. There's some problems with things like Gödel spacetimes, but we won't talk about that. Essentially, for the class of theories which have an admissible slicing of space into space and time, you can rewrite them as Hamiltonian. And you can rewrite the action as this ADM action, which has where we think about with Latin indices, G is a metric on a spatial slice, and pi is its canonical momenta, and these curly H's are the two constraints I talked to you about, these special functions that encode the symmetry. So this object here is a Lagrangian. The Hamiltonian is just
Is this the absolute value
of
n?
yes, because it doesn't have a sign.
Is that important?
No. I mean, you don't have positive. I'm not quite sure whether it is there because the elapse is constrained to be positive. So these n and this NA, so I'll talk about them a lot. N is a particular kind of multiplier function, and it's paired with the Hamiltonian constraint. NA is a particular, it's called the lapse, and this is another multiplier function. It's called the shift. It's three-dimensional, and it's paired with another kind of set of constraints called the momentum constraints.
This changing the sign of n would mean changing the sign of the metric. And that's kind of forbidden.
Yeah, so it's constrained to be one side. I think by convention you just always say it also means the direction in which you evolve slices forward. So they have quite the momentum constraint has quite a simple form. The Hamiltonian constraint has quite a complicated form. We won't actually, I think, need these equations again, but bear in mind that one of them is quite a long, complicated equation. One is quite a short equation, and you'll see this in the symmetry structure that they generate, and they're both functions of the canonical variables. You can then integrate them and smear them across a spatial slice, which we're going to call sigma, and get these kind of smeared versions of them. And they have, we can basically have Poisson bracket structure. So we basically have these two functions which are integrated across the slice and have these smearings, one relative to the n without the indice, one relative to the n with the indices. And the really important equation is the one I'm going to show you next, which is based upon these forms of constraints. And so we'll basically spend the rest of the talk just talking about this kind of algebraic structure. So we have two different families of two types of constraints. We have the momentum constraints and we have the Hamiltonian constraints. Right? If I tell you what they do, it'll start to be a bit clearer what's going on, how it relates to this idea of hypersurface. Really, the important thing is that the momentum constraints are the ones that tell you about changing coordinates on a spatial slice. Right? So they tell you how to move between one particular way of laying a spatial metric onto the slice and another. The Hamiltonian constraints are the ones that tell you, because they have this very complicated form, because the fact that they're really about how you can re-embed spatial hypersurface in a space-time. And so they have a much more complicated form, and they have a particular algebra. So this is just the Poisson bracket in this kind of Hamiltonian GR space. If you take two of the Hamiltonian constraints, their Poisson bracket will give you back a momentum constraint with this quite complicated term here, which involves the metric. If you take two Hamiltonian constraints two momentum constraints with each other, you get back a another momentum constraint, and this is the equation we'll talk about in a second. This final one is the most interesting one. You can take a momentum constraint with a Hamiltonian constraint, and you get back a Hamiltonian constraint. And we'll basically go through line by line this algebra. Technically, it's not an algebra because this is not a constant, it's a function, it's an algebroid, and try and understand what on earth this is. And I think the idea about time as a gauge transformation really comes from I'm trying to unpick what's going on here and whether it's actually quite as simple as a standard way of understanding these theories that was developed by Dirac. So we start with the easy one. We start with the spatial diffeomorphisms, the momentum constraints, and how to think about these as gauge transformations. And at least from my view, this isn't complicated or problematic, and the standard view on these transformations, these objects, is correct. Brian Pitts has argued it's not correct, if you want to have a dissenting view. But I think apart from Brian, I don't think anyone has a problem with this one. So the interesting thing about these is that you can actually show that they implement a Lie group of diffeomorphisms. You can actually think about the action of them like a Lie drag with this multiplier function, or with respect to this multiplier function. And in this kind of deformation language, you can think about this as a tangential deformation. So I'm deforming my hypersurface in a way that keeps my kind of spatial slice embedded into my chord geometry. So really what I'm doing is I'm laying down different spatial coordinates in my slicing of my space. And thinking about that as a gauge transformation doesn't seem like something you should be worried about. I'm basically saying if I have two possible descriptions of the world and I can map between them by changing the coordinates I put on a spatial slice, I should be really just I'm redescribing the same possibility. And this will hopefully bring to mind the whole argument to many of you. It really is almost exactly like the whole argument. So think about it this way: if you think about this surface as the spatial slice and this grid, this crisscross as the coordinates, what I'm doing is keeping the way that the surface is embedded in 4 dimensions the same, but I'm kind of deforming arbitrarily the way that the coordinates kind of laid onto that. And why am I saying this is like the whole argument? If I think about a curve in a space of possible canonical data, what I'm doing is moving between diffeomorphic related spatial canonical data. If I think about 2 curves that are initially the same, and then I hit some small section of them, I hit all the data in that section, or one representative of the curve with the diffeomorphism, I can get a different curve. So I get the kind of indeterminism or underdetermination, which I think is a better way of describing it, that you find in the whole argument. So I take some curve. So this is the phase space of Hamiltonian general relativity. This is the kind of submanifold where the constraints are satisfied, where all the action happens. I take some curve. I then hit some section of this curve, which corresponds to a sequence of 3 geometries with this diffeomorphism, and I get a different curve. So I find that I have an underdetermination, just like in the whole life. And the natural thing to do, this comes back to Niels's question, is to say, well, look, why don't we take the directions which I can access by these spatial diffeomorphisms to be gauge orbits? So all data on the orbit, on the dotted line, we take to be representing the same physical probability. And then I can kind of, I can either just identify those points or actually explicitly quotient out by those points and build a new representation which doesn't have the kind of seemingly problematic. And this is actually the kind of very general geometric procedure that's been developed since Dirac first introduced these ideas. And non-geometric terms, this is called symplectic reduction. Those of you interested in that. So you could take a symplectic manifold, take the constraint submanifold, take the orbits of the constraints, then quotient by these orbits and construct a new symplectic submanifold which doesn't have the redundancy. But you don't have to do that, right? You could also just say any 2 points in this orbit represent the same constraint, so the same possibility. I'm just going to keep track of those possibilities. In particular, when I define observables, I'm going to say the observables can't change when I go along those constraints. So I could describe a class of functions on this space, but I define them such that they don't change along these orbits. And so those are the things that really track possibility.
Okay, it just means redundant.
Yeah.
So gauge symmetry is a tautology. Well,
No, in the sense that a symmetry that's, I mean, in this sense, it's the local globe, right? So if I wouldn't be able to do this, that with a Leibniz shift, for instance, that would shift the whole thing. So it means, I think gauge symmetry means it's both, it's a symmetry and it's all the type of symmetry that I can apply it locally so that I can get it done. But in Dirac's terms, it actually means specifically the symmetry that has the geometric property of being generated by a constraint. So in fact, Dirac never uses the word gauge, but people take to be the Dirac criterion of gauge symmetry is to be generated by a first-class Hamiltonian constraint. And you can show that in most cases you get a nice equivalence between that and a local symmetry.
I'm not sure that everyone knows the whole argument. If you're going to use it in the next slides.
Oh, I won't go back to it. So if you don't know the whole argument, look up the whole argument. It's very interesting. It's basically an argument along similar lines that Einstein confused himself about, and then unconfused himself about, and then Ehrman and Norton confused everyone about, and we're still in the process of working out what many papers. But probably this Stanford Encyclopedia of Philosophy article is the best one. And in that, the argument really is that a particular view of ontology leads to this kind of undetermination problem, so we have to have a different view. But we won't talk about it. In fact, we will talk about it, but only here. So I wrote a paper actually making the comparison between the problem of time and the whole argument with Sean, some years ago now. And we were comparing it to a particular way of approaching the whole argument by Jim Weatherall, in what circumstances. Dirac, what I just said, Dirac proposed that observable quantities must have vanishing possible bracket with all first-class constraints, which is what I'm calling the dogma. And as I said, that basically just means if I'm an observable function, I can't change as I move in one of these kind of degenerate directions. And for the momentum constraint, eventually we get back to what we probably hoped in the end, that the observable functions have to be spatially diffeomorphism. So if I'm an observable function, I can't depend upon how spatial slice that we're talking about is coordinatized. And again, this physically seems very sensible because you don't want things that are observable to depend upon how we choose to put coordinates onto a spatial slice, because that's pretty arbitrary. We can use anything we want. We can move between different coordinatized representations of the same physical facts. We want our observables to be invariant in the right way. And as I said, you can think about this in a quite nice geometric way as projecting down onto a space where any 2 points like that project down into 1 point on the radius. So you get back a kind of correspondence between each point represents the center. This, so far so good. This is standard response to these kind of gauge symmetries. Works fine in electromagnetism. Works fine for the spatial constraints. It works fine. You can create little toy theories where you convert global to local symmetries, and you can do something like this for Leibniz shifts. What Barlow-Guattari is. Barlow-Guattari theory can be written in these terms, where this would then be a shift as spatial translation. All of this so far so good.
Yeah. So you're talking about observables. So assume the gravitational energy in general you would not count unless you're in specific ADM mass cases where.
That's a good question. Yeah, that's it. Yeah. But I mean, that's also difficult to define in this context because it depends upon the global structure, whereas here we're just dealing with local structure. Actually, that's really good and problematic. I think the slices would have to be compact as well. Okay, so what's the problem? Why am I going on about this? Right? The problem in particular is that whereas this bracket, we can really think about what's going on from this bracket, from theorems you can show for the momentum constraints, we can really think about it as a kind of a Lie drag along a particular direction. We can interpret how the momentum constraints is generating a symmetry at a time. It's much more complicated to be able to, in fact, I think it's not even possible in general to be able to unpick how this very complicated bracket, which describes what the Hamiltonian constraints of general relativity do, into an unproblematic kind of symmetry or dynamics.
So this second n should be n, right?
Second.
No, in the last term, it should be m d d n.
Yes, thank you. That must be true. Yes, sorry. Otherwise, it would make sense. The really important thing is actually this, the metric here. So the idea has always been that this first bracket encodes the deformations that are kind of not preserving the embedding of the spatial slicing. And these are often called refoliations. It would be easier if I had the whiteboard at this side. Can we write on these things?
Smart. Normally there's a flip chart. No, what is that? No.
So that should be right.
No. No.
It's okay. I can use a vivid metaphor.
Sorry.
So imagine you have a loaf of bread and you have a very boring bread knife and you slice the loaf of bread into slices. That would be a foliation, right? With the loaf is space-time, each slice is spatial time. What I could do is just get the bread knife and like say I'm really, really strong. I just bend it to like a funny, like odd shape. And then I cut the slices in this different way. And I could bend it each time I do a new slice. And so I just get this kind of weird refoliation, reslicing. And so the idea is that these first bracket, more complicated bracket, encodes reslicing. And it's a little complicated to show exactly how. Thébault does this by using this deformation. There's also a paper by Isham and Kukash where they do this by moving to a larger space where you can include extra parameters which tell you about how each street geometry affects larger geometry. I can just give you a little bit of my not entirely brilliant diagram where it's basically doing something like that's a very simple one. I'm kind of re-embedding the spatial slices. And so the idea is that this gives us formal determination again. We can think about this being one particular curve, this being another curve, and for that we slice the same, and then we smoothly implement a different slicing, and we get this kind of divergence. I'm informal at this stage. There's the intuition. This makes sense. So we expect to encounter this undetermination problem. So we're like, oh, let's implement the Dirac prescription. That worked really well last time. But then if we do that, I mean, there's lots of ways of unpacking this. But if we do that, what we find is that because the constraints themselves are also the Hamiltonian, theory, if we say the directions that they generate in phase space are gauge, we end up saying this strange idea that we mentioned right at the beginning, that time evolution is gauge, because time evolution is the direction general about the Hamiltonian. Time evolution, the direction by the Hamiltonian, corresponds to the directions that the Dirac prescription tell us. Gauge directions that we should have, for example, an observable function must have vanishing Poisson bracket with a first class constraint, one of these symmetry generating functions. If that's true, then the observable functions can't change in the direction picked out by that constraint. And if that's the constraint Hamiltonian, they can't change over time. It seems very strange, very confusing, in fact. And we find in the kind of the textbook on this, on constrained Hamiltonian theories, phrase which I used before, motion is the unfolding of a gauge transformation. States at different times are related by gauge transformation. We end up in, I think, quite a strange and serious problem. We end up like the time seems to have disappeared. That's rather confusing. There are two responses, I think, both of which are plausible, and one of which is held by most people, and one of which is held by Ian Shawn and a few other people. The first response is particularly developed by Carlo Rovelli, and it's to say, well, look, I think you just need to think more carefully about what time evolution really means. Really, what we think about by time is change in one set of physical variables with respect to another set of physical variables. So why don't we just accept the Dirac kind of prescription, then do some fancy footwork so that we describe evolution within this frozen formalism by basically taking one part of the physical variable and describing how that changed with respect to the other part. And classically, this actually works pretty well. Quantum mechanically, this leads to frozen wave function, and it's not quite so easy to get out of it. Some other problems that talk in a second. So I'm not claiming that the only response to the problem of time is just this picture, but it's not a response that I think is the best approach. In particular, with Shawn and I, in kind of middle of writing a 2-volume book. The first volume came out last year, available in all good bookshops. And but I mean, seriously, if you want to get a copy, just email me and I'll send you a PDF. You can also get it on Oxford Scholarship Online. Yes, that Utrecht will have access to. In any case, so in the book, we focused on the simpler case where you don't have the ability to kind of arbitrarily deform the slices. You just can move, in some sense, relabel a rigid slicing up and down, global reparameterizations. And what Shawn was able to prove is that you can explicitly separate out the thing that generates the relabeling of a kind of curve in time from the thing that generates the evolution. And there's no need to mix up evolution and gauge, and time is not gauge, time is time, gauge is gauge. He did this in a actually velocity phase space rather than a momentum phase space, because it's easier in that context. But you can make this identification for these theories where you essentially have a rigid slicing, but you can relabel the time like this. And so this approach, the second volume of the book, is how to deal with this problem in a more complicated case, where not only can you relabel time like this, you can also reslice. And this what I'm talking to you about today is our first kind of steps towards understanding that problem, and it will end up in the second volume of the book. And the approach starts from the final bracket. So the final bracket tells you how to relate a particular momentum constraint and a particular Hamiltonian constraint to a third Hamiltonian. So it actually tells you, in a sense, how to transform between Hamiltonian constraints using spatial diffeomorphism. It tells you how to reconstruct a Hamiltonian constraint by using a particular kind of application of a momentum constraint. And so what we're proposing is that we can actually use this extra structure given a particular Hamiltonian that generates time evolution. We can then build another Hamiltonian that will generate time evolution. And we want to treat these as generating the same time evolution, just the real time evolution. And our claim is that this is still within the spirit of general covariance, because we can always move to a different representation. The particular trick is very old. It goes all the way back to New York in the 1960s. It showed that you can find this special foliation called the constant curvature foliation, where the slices have a constant curvature, CMC, and there's a particular Hamiltonian in that slicing that you can use to generate evolution. And what's really nice is this connects very naturally to how physicists actually use general relativity to calculate evolution. This is the way that numerical, or a lot of numerical relativity will solve the initial value problem. The claim is we choose this foliation, we choose this, this is the Hamiltonian that we can use to generate the evolution of that foliation. We then use this third bracket to find a prescription to kind of move to the evolution generator in the other foliation. And this means that the evolution generator that we've got is kind of unique up to spatial diffeomorphism, because we identified these momentum constraints giving us gauge symmetry, giving kind of different ways of representing the same object. But what you have to do for this to actually work is actually pull the initial data along with you. And so we get back to a picture that's slightly different to the gauge symmetry picture. We basically think about curve in the space of three geometries with their data, canonical data. What we end up doing is not only is kind of moving to a new curve with new initial data, and then the claim is then that each of these we can use to reconstruct a space-time, and these space-times will be identical up to space-time difference. So we get two different representations of the same space-time, and each of them will carry along with it, given a slicing, a genuine Hamiltonian for generating the dynamics. So we don't have to kind of go up on time, and we don't even have to do the kind of clever Ravelli trick of using one physical degree of freedom to describe the others. So I've got 2 slides left. So there's three kind of, I think, nice features at least. As I said, we've got this natural connection to scientific practice in terms of numerical relativity, where they use the CMC foliation all the time. We don't have to do this deparameterization trick where we use 1 degree of matter. We use some kind of subset of the degrees of freedom to describe the evolution of the others. This is quite nice in kind of idealized situations, but in physical systems, we often find you have to switch which degrees of freedom are playing the role of the clock, which is problematic. And we also recover kind of the common sense understanding of the Friedmann equations, at least I think, where the Friedmann equations are evolution equations, which we use to describe the expansion of the universe. I'm actually working on a paper about this with Nicola Bamonti at the moment, really kind of responding to a paper by Thomas Thébault, where he really kind of bites the bullet and says, look, the Friedmann equations are just like the quote that I gave at the beginning. They are gauge equations that don't describe physical evolution, which seems kind of a radical re-understanding of cosmology. But there's always costs. So the actual construction of this Hamiltonian for anything other than the nice CMC slicing, it's very, very complicated mathematics, possibly not analytically tractable, certainly not in general, but even for specific cases. It isn't, there's some work needed to connect to some of Sean and I's other work on singularity resolution and the problem of time in cosmology. And we still have this complicated algebra, and so the problem of quantization is not going to go away just by having a nice way of describing the equation. Thank you very much.